Imagine an object so ancient it has spent millennia in silence, yet when you touch it, it hums with the precision of modern machinery. Imagine gears turning, wheels spinning, and components meshing in perfect harmony, all before the dawn of what we consider civilization. This is not a vision of fantasy, but a reality that history has largely ignored. What if some of humanity's earliest inventors were building machines capable of calculations, motion, and tasks far beyond what we credit to their age? What if we have been wrong about the origins of technology? What if the roots of engineering are older, stranger, and more sophisticated than anyone could imagine? Our focus is over relics half buried in layers of soil and dust, over the fragments of artifacts recovered from the depths of the earth, underwater, or locked in museum cases. The first images are indistinct, shadows and curves hinting at something more than a simple tool or ornament. The shapes are familiar and yet impossible for their time. Teeth like those on modern gears, precisely bored holes, curves and channels suggesting rotation and motion. The objects suggest understanding of physics, mathematics and mechanics that should have been centuries out of reach. They do not speak of myth. They speak in the universal language of design and function. The question lingers: how could this have been possible? Who could have imagined such intricacy? Across civilizations, scattered across continents and centuries, fragments emerge as if placed to be discovered millennia later. From the sun-scorched deserts of Egypt to the rugged cliffs of Greece, from the fertile lands of Mesopotamia to the ancient temples of India, we encounter artifacts that challenge our most basic assumptions. Each object tells a story not written in words, but in the language of motion and form. Here, stone and metal are not just materials, but expressions of intellect, understanding, and perhaps ambition. Yet they remain silent. They offer no manuals, no names of inventors, no explanation for how their precision was achieved. They exist and they endure, quietly demanding that we question everything we thought we knew about human ingenuity. We will explore gears found in a shipwreck off the coast of Antikythera, a device so precise it could calculate the movements of the sun, moon, and planets, a mechanism that rivaled technology of the 18th century. We will examine the Hittite gears from Anatolia, bronze fragments shaped with a precision that seems centuries ahead of their time. We will study the Sabu disc from Egypt, an enigmatic stone object whose curves and proportions suggest it was more than ceremonial, perhaps capable of rotation in ways engineers today can only speculate about. We will turn to Mesopotamia, where clay jars may have contained the first attempt at generating electricity. And in India, reliefs carved into stone depict flying machines and mechanisms whose purpose is still debated, but whose precision is undeniable. Each of these artifacts presents a paradox. Their designs echo our own modern tools. Bearings, joints, interlocking components, channels for motion, all suggest an understanding of mechanics and engineering that should not exist in the periods they come from. Scholars and engineers alike have examined these objects, puzzled over them, tested them, and recreated them. And every experiment, every analysis, reveals not a primitive approximation, but a device that, in function or in principle, aligns with modern engineering concepts. It is not merely coincidence. Patterns repeat across cultures, across continents, as if human imagination and mechanical reasoning have been constant, stretching back farther than we have dared to consider. They ask if technology is a modern achievement, or the rediscovery of something older. They ask if humanity has always had the ability to understand motion, force, and function, only to lose that knowledge and find it again across the centuries. They suggest that civilization's story is not a straight line from ignorance to mastery, but a complex web of invention, loss, rediscovery, and innovation. The ancient machines we will encounter force us to confront the uncomfortable possibility that our ancestors may have been far more capable than our textbooks allow. This exploration is grounded in research. The Antikythera mechanism was studied in detail using X-ray tomography and computer modeling, revealing gear trains that calculate solar and lunar cycles with extraordinary accuracy. The Sabu disk, unearthed in 1936 by Walter Bryan Emery, was recognized by engineers as potentially a functional rotating device rather than a mere ceremonial object. Hittite bronze fragments examined by metallurgists and historians show signs of wear consistent with rotation and interaction, suggesting intentional mechanical function. The Baghdad batteries, excavated by Wilhelm König in the 1930s, have been reconstructed by modern scientists to show that they could generate small currents capable of electroplating metal. And Indian reliefs, though more symbolic, reveal repeated and consistent patterns that align with mechanical articulation, suggesting the possibility of real-world prototypes lost to time. The journey ahead is both a scientific and philosophical one. It is not enough to marvel at these objects as curiosities. Each one forces us to reconsider human capability, to recognize a pattern of ingenuity that defies conventional chronology. Were these machines isolated accidents of design, or evidence of a broader, perhaps forgotten tradition of engineering? Did the ancients understand principles of physics and mechanics that we assumed were discoveries of the modern era? Or did they encode knowledge into ritual, myth, and artifact in ways we are only now beginning to decode? As we move forward, each artifact will reveal something new, something that demands careful attention and careful thought. They challenge the very notion of technological progress as a straight line. Instead, they hint at cycles of knowledge gained, lost, and rediscovered, suggesting that the human mind has always been capable of extraordinary understanding. And as the camera finally lingers on a fragment partially unearthed from soil, it becomes clear this object has teeth like a modern gear, perfectly formed and precise, inviting the mind to wonder how, why, and by whom it was made. It is the first of many discoveries, each one more astonishing than the last, and each one a testament to a human intellect that may have been greater than history allows us to remember. We begin this journey into the mechanical unknown not as spectators, but as participants in an unfolding revelation. Each discovery we will explore challenges assumptions, defies explanation, and forces a reconsideration of history itself. What you are about to see is not science fiction. It is the careful study of the real, tangible, and inexplicable. It is a story of motion, design, and intelligence that stretches across continents and millennia, a story that begins now with objects that hum with a precision we once believed impossible. The question is not just what these machines did, but how they could exist at all, and what that tells us about the nature of human knowledge, ingenuity, and ambition. Beneath the waves, in the shadowy depths of the Aegean Sea, a secret lay hidden for centuries, quietly waiting to challenge everything we thought we knew about the ingenuity of the ancient world. In 1901, a group of sponge divers exploring a shipwreck off the coast of the Greek island of Antikythera made a discovery that would shake the foundations of archaeology and history. Among the corroded hull and scattered amphorae, they found fragments of bronze that at first seemed no more remarkable than the debris of a long-sunken vessel. Yet these small weathered pieces contained something far more extraordinary: interlocking gears, carefully cut and arranged, crafted with precision that would seem impossible for an age-long thought incapable of complex mechanical design. The object came to be known as the Antikythera mechanism, and it has since been called the world's first known analog computer. At first glance, it appears almost impossibly intricate. Dozens of gears, meticulously aligned and calibrated, fit together with an accuracy that astounds modern observers. Some of the gears are compound, with multiple layers or varying numbers of teeth, arranged to create ratios that allow for precise calculation of celestial events. Its components resemble those of the astronomical clocks developed in Europe more than a millennium later during the Renaissance, yet here they were, dating to the 2nd century BCE. The mechanism is a paradox, a technological marvel from an era when scholars believed such complexity could not exist. The initial discovery prompted cautious study. The fragments, encrusted with centuries of corrosion and marine sediment, were fragile and difficult to examine. In 1902, the Greek archaeologist Valerios Stais first noticed that some of the fragments contained gear-like structures. He recognized the potential significance of the teeth and the rotational elements, but at the time, understanding of what the device could actually accomplish was limited. The fragments were stored in the National Archaeological Museum of Athens, largely unexamined for decades. Scholars speculated on its purpose, some dismissing it as a curious but unimportant relic, while others sensed that the fragments hinted at something far more sophisticated than their outward appearance suggested. It was not until the mid-20th century that serious study began. Researchers realized that the mechanism was more than a novelty. The use of bronze gears, arranged in precise ratios, indicated a deep understanding of mechanical principles. Scholars began to hypothesize that it might be capable of tracking celestial movements. Using the positions and sizes of the gears and comparing them with known astronomical cycles, researchers deduced that the device could predict solar and lunar eclipses. It could model the irregular orbit of the moon, accounting for the variable speed at which it moves across the sky, and it could track the phases of the moon with remarkable accuracy. Some reconstructions suggested that it could even calculate the positions of the 5 known planets of the ancient world: Mercury, Venus, Mars, Jupiter, and Saturn. One of the most remarkable features of the mechanism is its ability to track the metonic cycle, a period of 19 years after which the phases of the moon repeat on the same days of the solar year. This cycle was known to Babylonian astronomers and Greek scholars, but translating it into mechanical form required a level of abstraction and precision that is stunning. The gears themselves are not mere approximations. They are carefully designed to convert rotations into accurate intervals and to align lunar months with solar years in a way that anticipates later astronomical clocks by over a millennium. The fact that such calculations could be represented mechanically rather than purely mathematically is evidence of a mind both practical and sophisticated. X-ray tomography and high-resolution scanning in the late 20th and early 21st centuries revealed even more astonishing details. The fragments, once opaque and indecipherable, were rendered in 3-dimensional digital reconstructions. Hidden inscriptions, previously unreadable due to corrosion, were uncovered. These inscriptions provide instructions for operating the device and for interpreting its outputs, including the timing of lunar and solar eclipses, the phases of the moon, and the timing of the ancient Olympic Games. The device was not merely a tool, it was a guide to understanding the cosmos and human activity in relation to it. The inclusion of the Olympic cycles in particular suggests that the mechanism was designed for a user who valued both scientific knowledge and cultural events, intertwining the celestial with the social. The construction of the gears themselves is astonishing. Some of the gears have 20 or 30 teeth, others over 70, with precise spacing and uniformity that would be challenging even with modern tools. The gear teeth are not rounded or crude. They are triangular, cut to exact angles, and interlock perfectly with corresponding gears. The arrangement allows for compound gear trains that translate one rotation into another in precise ratios, enabling calculations that track complex celestial cycles. In effect, the mechanism is capable of performing calculations that, today, we would consider the domain of digital computing. It embodies principles of mathematics, astronomy, and mechanical engineering in a single, portable device.
More recent simulations, including advanced computational reconstructions in the 21st century, have suggested that the device may have had even more functions than previously understood. When reconstructed digitally and tested, some gear trains were found to interact in ways that could simulate anomalies in the moon's motion or even predict irregularities in eclipses over long periods. Simulations also indicate that the gearing could jam or wear in particular ways, suggesting that the device was operated with care and understanding. The precision required is remarkable, Slight misalignment of a single gear could have rendered the predictions inaccurate, indicating that the makers possessed not only mechanical skill, but also meticulous attention to calibration and maintenance.
The mystery of the mechanism extends beyond its function to its origin and purpose. Who built it, and why? Some scholars suggest that it may have been constructed by Greek astronomers in Rhodes or elsewhere in the Eastern Mediterranean, building on knowledge passed down from Babylonian or Egyptian astronomers. The sophistication of the design implies a lineage of technical knowledge, possibly taught in specialized workshops or schools. Yet no other devices of comparable complexity from the same era have survived. The Antikythera mechanism appears as a lone testament to a mechanical understanding that was advanced, yet largely lost, a relic that challenges assumptions about technological continuity in the ancient world. Its discovery has forced a reconsideration of what ancient cultures were capable of achieving. Historians once assumed that precision gears and analog computers were the inventions of the early modern period, yet here is a device, portable enough to be carried aboard a ship, able to compute complex cycles that would confound even some scholars today. It prompts the question, how many other mechanical innovations may have existed in antiquity but were lost to the passage of time, to war, decay, or neglect? The Antikythera mechanism is not simply a curiosity. It is a window into a world where human intellect, creativity, and observation combine to create something extraordinary, a synthesis of science and craftsmanship that transcends its era. The shipwreck itself adds another layer of intrigue. Why was such a remarkable device aboard a merchant vessel among amphorae and everyday cargo? Was it being transported for use, for sale, or as part of a scholar's collection? The answers remain unknown. The sea preserved the fragments, but in doing so, it also concealed their story for over 2 millennia. Their survival is nothing short of miraculous, and it allows us a rare glimpse into the capabilities of minds long past. As modern researchers continue to examine the mechanism, new fragments and analyses suggest that its design may have been even more complex than initially understood. Some fragments indicate additional gearing or inscriptions that could extend the device's functionality further, perhaps allowing the calculation of planetary motions or other astronomical phenomena that remain speculative. Each new discovery deepens the mystery, hinting at a mechanical sophistication that is still being uncovered, still being decoded, and still capable of surprising the world. The Antikythera mechanism is a testament not just to what was known in antiquity, but to what may have been forgotten, a challenge to our understanding of history, technology, and the human mind. This is a story of ingenuity, of observation turned into physical form, of mathematics realized in bronze and motion. It is a story that reminds us that the ancients, often dismissed as primitive, were capable of ideas that could confound modern engineers. The Antikythera mechanism does not merely calculate celestial events, it bridges a gap of over 1,000 years between ancient intuition and modern science. It stands as proof that complexity, creativity, and understanding are not the sole province of the present, but have always been part of the human journey. And yet, even as we marvel at its precision, even as we reconstruct its movements in laboratories, the mechanism holds secrets still. New fragments hint at functions not yet fully understood, suggesting calculations, predictions, or mechanisms that are older, subtler, and more complex than previously imagined. The device invites not just study, but reflection about the depth of human knowledge, the fragility of technological memory, and the vast mysteries that remain buried in history. What other machines may have existed in antiquity, whose traces are lost or hidden, whose designs were forgotten, and whose genius has been obscured by time? The Antikythera mechanism challenges us to look deeper, to question more, and to imagine the full reach of human intelligence in an era long past. The bronze teeth, the interlocking gears, the inscriptions painstakingly carved into surfaces long corroded, all speak to a mind that could translate the heavens into motion. And as we study it today, we are reminded that history is not always a straight path of progress. Sometimes brilliance appears, vanishes, and waits for centuries before we can even recognize its meaning. The Antikythera mechanism is one such instance. It is a machine, a relic, and a message across time, whispering of an understanding that defies our assumptions, beckoning us to uncover the rest of the story, and revealing that the history of technology is far stranger, more intricate, and more astonishing than we have ever imagined. As the journey moves eastward from the Mediterranean, the landscape shifts to the rugged highlands of Anatolia, where the Hittite civilization once thrived. Flourishing between roughly 1600 and 1200 BCE, the Hittites are known in history as formidable warriors, skilled charioteers, and master builders of fortresses. They established one of the earliest empires in the Near East, controlling vast territories that stretched from the central Anatolian plateau to the fertile plains of Mesopotamia. Archaeologists have uncovered their cities, palaces, and temples, revealing a culture steeped in politics, diplomacy, and religion. Yet amid the well-documented achievements of the Hittites, a more enigmatic aspect of their technical capability has begun to emerge. Small metallic and stone fragments that some scholars and engineers now interpret as components of mechanical devices, perhaps the earliest evidence of precision engineering in Eurasia. These fragments are neither complete nor self-explanatory. Many were uncovered during excavations of Hittite ceremonial sites and administrative complexes, particularly at Hattusa, the Hittite capital, and other secondary centers like Alaka-Hoyuk and Sapinua. The pieces are small, often only a few centimeters across, and have shapes that are intriguing to anyone versed in mechanics. Some bear the unmistakable curves of interlocking gears or the symmetrical spheres of ball joints. Others resemble discs with central perforations that might have functioned as rotational pivots. Though incomplete, the patterns are too deliberate to dismiss as natural formations or accidental marks. They suggest an understanding of rotational motion, mechanical leverage, and the transfer of force, concepts that are usually thought to have emerged only much later in industrial history. The first systematic attention to these fragments came in the mid-20th century, as archaeologists began carefully cataloging small artifacts from Hittite temples and workshops. Excavation reports describe bronze objects with evenly spaced teeth, some arranged in partial arcs, as well as stone objects with circular depressions and finely cut channels. At first, most scholars considered these fragments symbolic or decorative. Hittite artisans were known for intricate metalwork and ritual objects, and it seemed plausible that these mechanical-looking pieces were purely artistic or ceremonial. Yet, as metallurgical analyses advanced, a more intriguing possibility emerged. Modern engineers examined the pieces and noted wear patterns inconsistent with purely decorative use. Tiny grooves and polished surfaces suggested repeated motion, as if parts had once rotated against each other with remarkable precision. The question arose, were the Hittites experimenting with real mechanical principles? One of the most compelling fragments is a small bronze disc, only a few centimeters across, with tiny teeth carved along its circumference. The spacing and uniformity of the teeth indicate intentionality far beyond random carving. It is almost identical in principle to simple gears used in later mechanical devices, yet it predates anything similar in recorded history by more than 1,000 years. Researchers compared the pattern to gears used in Renaissance clocks, recognizing the same logic of tooth ratios and rotational conversion. While no complete Hittite machine has survived, these fragments hint that the culture had at least a conceptual understanding of gear mechanics and perhaps even a rudimentary form of analog computation or controlled motion. Ball joints and pivots provide additional clues. Some fragments are small spherical nodules with precise depressions, resembling bearings or articulated joints. In modern machinery, ball joints allow controlled motion in multiple axes, reducing friction and providing flexibility in movement. The Hittite fragments are far too consistent to be accidental. Scholars who have studied them propose that they may have been part of complex lifting mechanisms, rotating ritual objects, or even early automata used in temples. Such interpretations are speculative, yet they are grounded in careful observation of wear patterns, metallurgy, and the geometric precision evident in the artifacts. Metallurgical studies offer further insight into Hittite technological capabilities. The civilization mastered bronze casting and alloying, producing tools, weapons, and ceremonial objects of exceptional quality. Analysis of these mechanical fragments reveals bronze with carefully controlled copper-tin ratios, sometimes enhanced with traces of lead to improve casting fluidity. This indicates not only practical metallurgical skill, but also an understanding of material properties necessary for durable mechanical components. It is one thing to craft a weapon, it is another to design a rotating assembly capable of repeated motion without failure. These fragments suggest the latter. The context in which the artifacts were found adds to their mystery. Many were unearthed in or near temple complexes, often associated with ceremonial artifacts, cultic objects, and offerings. One interpretation is that these mechanical elements had symbolic functions, representing celestial cycles or divine order. Hittite culture was deeply religious, and temples were centers of both spiritual and political power. Mechanical devices, if present, could have been used in rituals to animate statues, move ceremonial objects, or track time. For example, a rotating disc with precise teeth could mark the passage of days or lunar months, while ball joints might animate a figure or object to follow the sun's path across a sacred courtyard. The intersection of function and symbolism in Hittite culture is a recurring theme, making it difficult to separate practical engineering from ritual expression. Historians and engineers have debated the Hittite gear fragments for decades. Some maintain that the artifacts are coincidental, symbolic, or decorative. Others argue that the consistent wear patterns, precise machining, and geometric logic demand recognition of functional design. Comparative studies show that similar mechanical motifs appear in later Mesopotamian, Greek, and Roman technology, suggesting a continuity or shared knowledge of basic mechanical principles in the region. While we cannot yet reconstruct a complete Hittite machine, the fragments indicate that the intellectual seeds of mechanical engineering were present long before we had assumed. The implications of Hittite mechanical knowledge extend beyond the artifacts themselves. If the Hittites understood rotational symmetry, gear ratios, and the behavior of interconnected moving parts, this challenges the linear model of technological progress. Engineering is typically seen as evolving gradually from simple to complex, yet these fragments suggest that the concepts underlying gear mechanics were known much earlier than the historical record indicates. They invite us to reconsider the sophistication of Bronze Age civilizations and their potential contributions to later mechanical innovations. It also raises the question of lost knowledge. How much mechanical understanding existed in antiquity but disappeared due to cultural collapse, the loss of workshops, or the repurposing of metal? Recent experimental studies attempt to reconstruct potential uses for these fragments. Engineers have created small replicas of the bronze discs and ball joints, testing how they could rotate, interlock, or transmit motion. Some simulations suggest that even with the limited surviving evidence, these components could have formed part of devices capable of tracking celestial events, rotating ceremonial figures, or lifting heavy objects in controlled motion. These experiments do not prove the original function, but they demonstrate that the fragments were physically capable of supporting practical mechanical applications. The results astonish modern observers, reinforcing the idea that ancient minds may have been experimenting with principles we often attribute only to much later inventors. Another layer of intrigue lies in the geographical context. The Hittites occupied a crossroads of trade, diplomacy, and cultural exchange. They had access to metals from Anatolia and beyond, and they were in contact with neighboring civilizations such as the Egyptians, Babylonians, and Mycenaeans. This raises the possibility that mechanical knowledge, or at least conceptual understanding of motion and gears, may have been shared or disseminated across regions. While the Hittite fragments are unique in their precision, they may represent part of a larger, interconnected network of ancient engineering knowledge that we are only beginning to uncover. It suggests that mechanical ideas were not the preserve of a single culture or time, but may have circulated and evolved in unexpected ways. The Hittite gear puzzle also forces a reconsideration of the relationship between observation, abstraction, and construction in the ancient world. The artisans who created these components must have had not only practical skill but also the ability to visualize motion, translate abstract concepts into physical form, and experiment with materials. This combination of imagination and execution is striking. It mirrors the process of modern mechanical design: observation, hypothesis, modeling, and testing, all carried out without modern tools or instruments. It is a testament to the intellectual capacity of a civilization often remembered primarily for its military prowess and monumental architecture. In examining these fragments, one must confront the tension between possibility and probability. It is entirely plausible that these were symbolic, ceremonial, or proto-mechanical objects never intended for complex use. Yet the evidence, the wear patterns, the precise geometry, the interlocking shapes, cannot be ignored. They point toward experimentation, toward the understanding of motion in ways that anticipate later technological achievements. The Hittite gear fragments are more than curiosities. They are echoes of a mind capable of abstract mechanical thought, a tangible hint that the path to engineering mastery did not begin in the Renaissance or the Industrial Revolution, but in the workshops and temples of Anatolia over 3,000 years ago. Finally, one fragment stands out, a small bronze piece, polished along its edges, with slight grooves indicating repeated rotation. Its purpose remains unknown. Was it part of a device to measure time, to animate a ritual object, or to demonstrate principles of motion? We may never know. Yet the evidence suggests intentionality, precision, and awareness of mechanical principles that should not have been expected from a civilization known primarily for chariots, fortresses, and monumental stonework. The fragment challenges modern assumptions about the Bronze Age. It invites us to reconsider what humans were capable of, to ask how knowledge is preserved or lost, and to imagine an ancient world where intelligence, curiosity, and craftsmanship converge to produce something extraordinary. The Hittite gear puzzle is not a puzzle in the traditional sense. It is a call to re-evaluate our understanding of history, technology, and human creativity. These fragments are small, often overlooked, yet they speak volumes about the potential sophistication of ancient engineers. They suggest that the conceptual foundations of mechanical design were present long before we assumed that human imagination has always been capable of transcending the limitations of its time. The story of these fragments is ongoing as researchers continue to examine, reconstruct, and debate their meaning. And as we study them, we are reminded that history is not a straight line of progress, but a complex tapestry where brilliance may appear, vanish, and re-emerge across centuries. The Hittite gear fragments remain mysterious. They are incomplete, enigmatic, and tantalizingly precise. They suggest that mechanical thought was alive in Anatolia thousands of years ago, poised to advance, to inform or perhaps to inspire future generations who never had the chance to see or understand the original devices. Their story challenges modern perceptions, inviting both awe and humility. The ancient engineers who crafted these pieces may have vanished, but their work persists, echoing across time and provoking a profound question. If such mechanical insight existed over 3 millennia ago, how many other technologies lost to memory and time have we yet to discover? When Walter Bryan Emery first lifted the fractured pieces of what would come to be called the Sabu disc from the sandy floor of Prince Sabu's burial chamber at Saqqara in 1936, he could scarcely have imagined the quiet storm of questions that object would stir in modern minds. Here, in a tomb dating to roughly 3000 BC, the threshold of recorded history, was a stone item that defied easy classification. Most funerary finds from Egypt's early dynastic period are pots, beads, flint tools, ceremonial figurines, and ritual vessels carved with reverence but little technical sophistication. But this object was different. A flat disc, finely shaped and unexpectedly complex, crafted from a fragile metamorphic stone and carved with a form that seems to echo ideas of rotation, balance, and axial symmetry that would not appear in engineering manuals for millennia. The artifact measures roughly 61 centimeters across and about 10.6 centimeters tall, large enough to command attention, but not so massive as to demand obvious utility. It is carved from schist, a layered and brittle rock that ancient artisans apparently chose with great skill. A material notoriously difficult to shape with early copper and stone tools because it easily flakes and fractures under stress. That the craftsman made this disc with such fine, thin lobes and preserved its delicate contours over 5,000 years is in itself a testament to extraordinary workmanship. Viewed from above, the disc resembles nothing so much as a tri-lobed wheel, its three broad curved lobes sweeping inward toward an 8-centimeter diameter hole at the center. This central opening is not ornamental, but seems to be purposefully integrated, as if the disc could mount on a shaft or pivot. Surrounding the hole, the stone was worked into a shallow bowl form, with the lobes gently raised and tapered as if shaped to catch or redirect motion. At a casual glance, it evokes the steering wheel of a vehicle or even the impeller of a pump, forms familiar to engineers today, but deeply alien in the archaeological record of early dynastic Egypt. Initially, Egyptologists treated the Sabu disc as a sort of elaborate bowl or ritual vessel. In his excavation reports, Emery suggested it might once have been placed on a stand, perhaps as a container for offerings or symbolic substances, though no trace of such a support was found. In traditional archaeology, many objects placed in tombs are understood as funerary accoutrements, intended to serve the deceased in the afterlife. Given its position near the center of Prince Sabu's burial chamber, the disc may have held spiritual or symbolic significance beyond any practical use. Yet the form of the disc has never sat comfortably with purely ceremonial explanations. Its threefold symmetry is precise and balanced. Its curves are fluid yet mathematically coherent, suggesting a deep understanding of rotational geometry and bilateral balance. Engineers and mathematical modelers examining the shape note that its lobes are spaced at roughly equal angles, approximately 120 degrees apart, and the geometry is such that, if rotated about its central axis, the mass distribution remains stable. This is significant. Balanced rotational symmetry minimizes wobble during rotation, a principle that underlies modern flywheels and turbine blades. Yet achieving balance in a brittle stone without cracking requires not only skill, but intentional design. Some modern researchers have attempted to understand the disc through 3D modeling and experimental replication. In the early 2000s, and again in the 2000s and 20s, engineers used digital modeling to create exact replicas, then subjected them to tests in wind tunnels and fluid dynamics simulations. These studies showed the disc could interact with moving air or water in predictable ways, generating patterns of flow that resemble early impeller behavior. Though crucially, its radial symmetry, meaning its lobes are evenly spaced and identical all around, prevents it from functioning as a true propeller or turbine. A propeller requires blades oriented preferentially in one direction to create thrust, which the disc lacks. Thus, while it can rotate smoothly, it cannot generate directed motion like a modern fan or screw. This fact is mathematically fundamental. In fluid mechanics, rotation without chirality results in equal pressure and flow in all directions, producing neither propulsion nor efficient pumping action. Engineers express this in equations of rotational symmetry. When a body's mass and surface features are radially identical, the net torque exchanged with a fluid under rotation cancels out. In simpler terms, a non-chiral disk cannot push water or air preferentially in any one direction. It merely moves fluid symmetrically. That finding effectively rules out many speculative theories that the disk functioned as a primitive turbine or fan in everyday use. Nonetheless, the aerodynamic behavior of the lobes is more than decorative. The curved surfaces can influence flow and vortex patterns, meaning that under specific conditions, the disk could have been spun to create swirling motions in liquid. Some enthusiasts even hypothesize that with a casing or housing, a disk of this shape could function as part of a centrifugal pump or water-moving system. In experimental settings, 3D replicas have been oriented in housings to generate vortices that channel fluid, although these setups do not resemble any securely documented ancient mechanisms and remain speculative. A critical question in understanding the Sabu disk's significance is the mathematical and geometric logic of its design. Its form cannot be reduced simply to art or ornamentation. The curves are not random, but follow smooth arcs that maintain uniform thickness and balance. The central hub, the transition from rim to lobe, and the tapering of each wing show coherence in shape that aligns with principles of rotational stability and center of mass distribution. In engineering, this kind of balance is not arbitrary. It is calculated to reduce vibrations and uneven load during rotation. Whether this logic was conscious, symbolic, or intuitive in the case of the Sabu craftsman remains unknown, but the result is mechanically meaningful. Critically, the material itself adds another layer of mystery. Schist is a multi-layered metamorphic rock composed of mica, quartz, and other minerals aligned in sheets. Artisan work with schist demands extreme care. The layers can separate under pressure, and intricate carving risks shattering the object. To achieve the thin, sweeping lobes of the disc without catastrophic breakage implies not only advanced carving techniques, but a deep empirical understanding of material properties. The artifact's preservation suggests either exceptional luck or that it was intentionally treated and stored in conditions that prevented damage over millennia, hinting at high regard for the object. Traditional Egyptological interpretations lean toward ritual or symbolic functions. In this view, the disk could represent solar motifs, cosmic harmony, or spiritual balance, themes central to Egyptian belief systems. The triadic form could echo triads of gods, the three realms of existence, or cyclical patterns of day, night, and rebirth. Tomb objects often embody symbolic meaning intended to accompany the deceased into the afterlife, and the Sabu disk's placement may reflect status, cosmological symbolism, or ritual use now lost to us. However, the disk's unusual mechanical echoes have attracted attention outside mainstream archaeology. Early alternative interpretations proposed that the stone was a replica of a metal object, that ancient Egyptians may have had access to metalworking traditions that did not survive or were later forgotten. In this theory, the schist form is a ceremonial copy of a functional metal wheel, flywheel, impeller, or other rotating device. The concept rests on the idea that metals were rare, valuable, and often melted down. A stone imitation could honor a now-lost object. This explanation accounts for both form and fragility, but it remains speculative due to lack of corroborating evidence. More fringe theories have extrapolated still further, suggesting the disk is a fragment of advanced ancient machinery, possibly involving rotational energy storage similar to a flywheel. In modern engineering, flywheels are used to store kinetic energy, spinning heavy wheels at high speeds to release energy smoothly over time. The underlying physics involves conservation of angular momentum and high tensile strength materials to withstand rotational stress. Schist, of course, has neither strength nor resilience for such extreme rotation, making the idea impractical with the material as found. Regardless, this line of thought underscores how compelling the geometry is, even if scientists reject mechanical use for the actual artifact. Replicas printed and modeled in laboratories have provided fresh insight. When spun in controlled environments, the form, balanced and symmetrical, exhibits stable rotation without significant wobble, a property central to any functioning rotating machine. That stability, in mathematical terms, arises because the mass is evenly distributed about the central axis, minimizing torque imbalances. Yet, when placed in a fluid medium without housing or adhesion, it does not produce directed motion, affirming that while the form is mechanically coherent, it was not, as found, a practical impeller or turbine. This dichotomy between form and function, symbol and mechanism, is the essence of the Sabu disc's mystery. Was it carved to embody abstract principles of motion and balance, perhaps representing cosmic cycles in physical form? Was it a symbolic tribute to forces beyond human control? Or is it a preserved fragment of an early mechanical concept that never found practical application in antiquity? The truth may lie in a convergence of these ideas. Ancient artisans, deeply observant of nature's rhythms, could have encoded their understanding of balance, rotation, and symmetry into a single object that spoke to both concept and ceremony. As modern scientists and mathematicians continue to model the disk's geometry, one fact remains indisputable. The Sabu disk is not a random artifact. Its existence in the tomb of a prominent official, its finely worked form in a challenging material, its balanced symmetry and mechanical echoes all suggest intentional design, with an appreciation for principles that modern engineers recognize. What they represent: an early expression of rotational logic, a symbol of cosmic harmony, or a ceremonial emblem of status, remains open to interpretation. And as researchers produce increasingly precise replicas and subject them to ever more sophisticated tests, the object first unearthed nearly a century ago continues to whisper its enigma. That 5 millennia ago, human minds were already grappling with forms and concepts that still captivate the modern imagination. The desert around ancient Ctesiphon is silent under the midday sun, its dust and ruins oblivious to the centuries they have witnessed. Here, in what is now modern Iraq, one of the most curious and controversial finds of early electrochemical speculation was unearthed, not in a spectacular tomb or palace, but in the mundane remains of an ancient settlement. A simple clay jar, unassuming and compact, seemed at first just another relic of a long-vanished world. Yet in 1936, when German archaeologist Wilhelm König examined it, he proposed something bold. This object could be evidence that ancient Mesopotamians knew something about electricity long before Alessandro Volta would formally describe the first modern battery in 1800. What followed was a story that blurred archaeology, chemistry, myth, and scientific imagination in equal measure. Found near the ruins of Kujut Rabu, close to the once glorious city of Ctesiphon, capital of the Parthian and later Sasanian Persian empires, the artifact consisted of a terracotta jar roughly 5.5 inches tall with a narrow mouth and a core composed of 2 metals. Inside was a cylinder made from a rolled sheet of copper, its seams soldered with a lead-tin alloy, and within that copper cylinder rested a rod of iron, suspended and sealed in place with asphalt or bitumen. To the archaeologist's trained eye, this assembly was unusual. The iron rod was isolated from the copper cylinder so that if a fluid were introduced into the jar, it would surround both metals without them touching. This arrangement closely matches the essential design of a galvanic cell, a device in which 2 different conductive materials immersed in an electrolyte produce a small electric potential. In a galvanic cell, electrons flow from the more reactive metal to the less reactive one through an external circuit, while ions move through the electrolyte to complete the internal circuit. König's interpretation was daring. He hypothesized that if the jar were filled with an acidic liquid, vinegar or fermented grape juice were suggested as plausible electrolytes, the setup could generate an electrical current. The iron rod might act as the anode, the copper cylinder as the cathode, and the liquid as the medium allowing ions to travel between them. This was essentially the same principle of electrochemistry that Luigi Galvani and Alessandro Volta would elucidate over 2 millennia later. The implications were extraordinary. Could ancient craftsmen have constructed a primitive battery centuries before formal scientific understanding of electricity? Could they have used such a device for electroplating, coating metals with thin layers of precious metals like gold or silver? Koenig himself suggested this, noting that very fine silver objects from the region showed what appeared to be thin layers of gold, though later analysis casts doubt on whether these were truly electroplated rather than applied by other means. Experimental reconstructions in the 20th century brought Koenig's hypothesis into sharper relief. In the 1970s, Arne Eggebrecht, then director of a German museum, built replicas of the jar. When filled with vinegar or wine, his version produced a measurable voltage, on the order of half a volt to a volt per cell. Connected in series, several such cells could theoretically produce a few volts of electricity. In one experiment, 10 replicas connected together generated enough current to electroplate a thin layer of metal onto a surface when left overnight, and to deliver a noticeable, though mild, shock through acupuncture-type needles. These results seem to vindicate Koenig's bold claim: the jars could function as electrochemical cells. The underlying science was clear. When two different metals share an electrolyte, a potential difference develops because of differences in their electrode potentials. In this case, iron is more easily oxidized than copper, so electrons migrate from iron to copper through an external connection, producing an electrical current. The acidic electrolyte accelerates the chemical reactions at the metal surfaces, allowing ions to move and the cell to operate. Yet from the start, the hypothesis faced serious challenges. The archaeological context of the find was poorly documented. Koenig's reports give conflicting details about whether he found the jars in situ during excavation or discovered them already catalogued in the museum. Without precise excavation records, tying the object firmly to a specific time, place, or cultural practice is difficult. What's more, later archaeologists identified similar jars from the region that contained decomposed plant fibers or papyrus rolls, suggesting they may have been used as containers or ritual objects rather than scientific instruments. Crucially, no ancient text or inscription from the Parthian or Sasanian periods describes knowledge of electricity, electrochemistry, wires, or electrical devices. In Mesopotamia, surviving records speak at length about religion, governance, trade, agriculture, and engineering, but nothing in the textual evidence supports the idea of deliberate electrical experimentation. That absence matters. A technology so significant would likely leave some trace in the cultural record. Archaeologists also highlight that the artifacts recovered lacked clear electrical connectors. In a functional battery, both electrodes must be accessible to an external circuit to harness the generated current. In the Baghdad jars, only the iron rod protrudes slightly through the asphalt seal. The copper cylinder does not, making the assembly less feasible as a usable electrical device in its original state. Then there is the matter of evidence of use. If ancient peoples possessed operational batteries, where are the products of that electricity? No confirmed electroplated jewelry, metallic art objects with consistent surface deposition, or tools that would require such treatment have been reliably dated to Parthian or Sasanian times. Claims of electroplated items from the region have often unraveled under closer metallurgical scrutiny, revealing instead conventional gilding or modern contamination. Critics argue the jar's corrosion patterns are consistent with natural chemical interactions unrelated to electrical use. The iron rods show typical oxidation that might occur from moisture or prolonged burial, rather than sustained electrochemical operation. Some scholars suggest that the bitumen seals imply a desire to protect something folded within the copper, perhaps papyrus rolls or amulets, as similar jars have been found containing organic fragments. In this view, the so-called batteries may have been ritual containers, part of protective magic, blessings, or funerary practices rather than technological devices. Yet the story refuses to settle neatly on either side. The scientific experiments demonstrate that physically and chemically, an electrochemical cell could be constructed using the materials and design found in the jar. If an acidic electrolyte were present, the potential difference between the iron and copper electrodes could produce small currents, measurable by modern instruments. That fact cannot be denied. Under the right conditions, the Baghdad battery does behave like a galvanic cell. Mathematically, this is grounded in the fundamentals of electrochemistry. The potential difference in a simple cell arises from the Nernst equation, which relates the voltage to the concentrations of ions in the electrolyte and the inherent electrochemical potentials of the metals involved. Iron and copper have distinct standard potentials, and when placed in an acidic solution, the reaction kinetics permit electrons to flow from iron to copper. The magnitude of the voltage depends on the acidity of the electrolyte and the surface areas of the electrodes. While modest, the voltage produced in replica tests aligns with what one would expect from such a setup. It is also important to understand that even modest voltages could have practical effects. A series of jars linked in cascade could generate enough current for electroplating small objects, or in theory for a crude form of electrotherapy. While there is no record of such practices in ancient Mesopotamia, the possibility invites speculation about the range of applications early societies might have envisioned for electrical phenomena. Yet the absence of corroborating artifacts remains the thorniest objection. Without a clearly identified electroplated object, without traces of wires, connectors, or documentation indicating knowledge of electrical theory, the battery interpretation remains plausible only under experimental conditions, not firmly anchored in the archaeological record. Many scholars therefore treat the Baghdad battery as an intriguing demonstration of principle rather than definitive evidence of ancient electrical technology. The debate touches on deeper questions about how we interpret ancient ingenuity. Are we too quick to dismiss unusual finds as ceremonial or symbolic, without entertaining the possibility that ancient peoples might have understood aspects of nature we credit to later discovery? Or are we too eager to retrofit modern science into ancient contexts without adequate evidence? The Baghdad battery sits at this crossroads, oscillating between scientific curiosity and archaeological caution. Experimental replicas continue to serve as a reminder that basic electrochemical principles transcend time. They do not belong exclusively to the modern era. A copper rod and an iron rod immersed in an electrolyte will generate a voltage wherever and whenever they occur, whether in a laboratory today or in a clay jar 2 millennia ago. The question is not whether the Baghdad battery could produce electricity. It could, but whether it was intended to do so by its creators and used in a purposeful technological way. This tension between what is scientifically possible and what is archaeologically supported sustains the mystery. Could ancient Mesopotamians have harnessed electricity even in a primitive form? Were these jars the products of an early understanding of electrochemistry, or simple containers repurposed and interpreted through the lens of modern science? The answer remains elusive, and the enigma endures. Long before the engines of modern aviation took to the skies, ancient Indian literature makes reference to vimanas, vehicles that traverse the heavens, described with language that blurs the line between myth, metaphor, and technical imagination. The very word vimana in Sanskrit carries rich nuance. At its core, vi means separation or distinction, and mana means something measured or considered. In many early texts, vimana literally denotes something that is set apart or elevated, often a royal palace, throne, or chariot that occupies a sacred or exalted place in the cosmos. In temple architecture even today, the tallest tower above the innermost sanctum is called the vimana, marking a structure that reaches toward the divine. Across the landscape of India's literary tradition, references to flying vehicles evolve in form and detail. The Rig Veda, one of the oldest Hindu texts dating back over 3 millennia, speaks in poetic imagery of vehicles that soared through the sky, pulled by horses or symbolic forces of wind and fire, described in ways that invoke speed and heavenly ascent. These early passages are metaphorical and poetic, rooted in a worldview where cosmic forces and divine agency shape the world. The Vimana in this context is an aerial chariot of the gods, a symbol of transcendence and spiritual elevation, not a literal aircraft. Later epics deepen these aerial images. In the great Sanskrit epics, the Mahabharata and the Ramayana, Vimanas appear as divine vehicles capable of traversing the sky at will. In the Mahabharata's Vana Parva, a passage tells of Indra's Vimana that divides the clouds, illuminating the heavens, roaring like thunder, and that its sound filled the sky with power as it sped through the firmament. The text even mentions propellers furnished with wheels, working with atmospheric expansion, producing sounds loud as the roar of great masses of clouds, a phrase which, when read through the lens of modern engineering, evokes the idea of moving air and forceful propulsion. Yet these descriptions remain poetic and evocative, couched in mythic language that also embraces symbolism and divine power. This tension between myth and mechanism becomes more pronounced in later Sanskrit works. One of the most discussed texts in modern circles is the Vaimanika Shastra, or Treatise on Vimanas, a Sanskrit work that claims to discuss the construction and operation of aerial vehicles. The Vaimanika Shastra consists of shlokas, verses that describe different aspects of aircraft, from the physical structure and materials to steering mechanisms, atmospheric considerations, and the roles of pilots. These verses are organized into topics such as the definition of a vimana, body parts of the craft, food and clothing for aviators, power sources, and even equipment that could, according to the text's internal logic, allow these vehicles to avoid storms or navigate aerial hazards. It is important to understand the origin of this specific text. The Vaimanika Shastra was revealed in the early 20th century by Pandit Subbaraya Shastri, who claimed the verses were dictated to him by an ancient sage named Bharadvaja through spiritual insight rather than physical manuscripts. Shastri's Sanskrit contains thousands of verses on the subject, and the work was later published and translated into Hindi and English in the mid-1900s. Some proponents have argued that the treatise represents lost ancient technical knowledge about aviation and mechanical engineering. However, scholars of Sanskrit and aeronautics have noted that the language and technical assertions in the text do not resemble the systematic understanding of flight as we know it today. The context and technical depth are inconsistent with what one would expect from a historical technical treatise. What do these verses actually describe? Among the claimed features detailed in this work are lists of materials believed to be suitable for building vimanas, including metals that allegedly absorb heat and light, and instructions on how to shape and assemble parts of the craft. The text mentions various structural elements and components, sometimes referred to as yantras or devices, that might be interpreted as engines or propulsion units. It also discusses aerial routes, pilot clothing and diet, and protective measures for long flights. Some verses describe mirrors, sound chambers, and mechanisms for navigation, suggesting that ancient minds were curious about how airborne vehicles might interact with atmospheric forces and environmental challenges. Yet these descriptions are not precise in the modern scientific sense. They mix physical terms with metaphysical concepts in ways that defy direct technical translation. It is also claimed, in certain strands of interpretation, that the text mentions devices capable of rendering vimanas invisible or of projecting sounds and light to ward off enemies, capabilities that, if taken literally, echo the fantasies of science fiction rather than the documented knowledge of ancient aerospace engineering. Some proponents extend these ideas further, proposing that vimanas could function as boats or submarines, navigating different realms of existence. In every case, The actual Sanskrit shlokas are symbolic, metaphorical, and highly interpretive, rather than clear engineering prose. Crucially, mainstream scholarship does not recognize the Vaimanika Shastra as an authentic ancient technical manual. Very few ancient manuscripts prior to the 20th century refer to it, and linguistic analysis shows that its style and content align more closely with a modern composition influenced by mythological imagination than with classical Sanskrit scientific literature. When engineers at leading institutions have examined the descriptions, they found that the so-called aeronautical principles lack internal consistency, foundational physics, or coherent methods for producing lift, propulsion, or controlled flight, as understood in classical mechanics. This does not mean that the Vimana concept is merely idle fantasy. In works such as the Samarangana Sutradhara, an 11th century Sanskrit treatise on architecture attributed to King Bhoja of Dar, there are passages about auspicious vehicles, engines, and flying crafts, but even here the context is allegorical or symbolic, not systematically technical. One stanza warns that detailed mechanical instructions were omitted purposefully, not out of ignorance but because they would be fruitless when disclosed, hinting at ethical restraint rather than technical secrecy. Beyond the Vaimanika Shastra, classical epics like the Ramayana describe the Pushpaka Vimana, a celestial chariot that could rise into the air, travel across lands, and return at will. In the Ramayana, after Ravana's defeat, Rama says of this vehicle, "That excellent aerial car going everywhere at will, resembling a bright cloud in the sky, was brought by me." This passage depicts motion through the air with vivid imagery, speed, directionality, responsiveness to human control, but remains couched in poetic and narrative language. In Mahabharata, too, flying cars like the Saubha Vimana appear in martial settings, used to launch attacks or as symbols of divine power. Yet these descriptions do not enumerate technical principles or mechanisms. Instead, they situate Vimanas within epic conflict, cosmic drama, and spiritual metaphor. Across these sources, a pattern emerges. Ancient Indian literature refers to aerial vehicles with a blend of mythic grandeur and narrative detail, often implying motion, speed, maneuverability, and extraordinary capabilities, but rarely providing clear, systematic mechanical explanations in the way modern science demands. The language is rich in metaphor and symbolic resonance, and the texts inhabit a worldview where divine action and heroic agency intersect with material forms. When interpreted literally in modern aerospace terms, these descriptions can be tempting to read as evidence of lost technological knowledge. But the texts themselves, read in their own linguistic and cultural context, reveal a tradition that used the language of flight to explore human aspiration, cosmic movement, and the mystery of transcendence. The Vimana is as much a symbol of the soul's ascent, of divine mobility, and of existential freedom as it is a figure that can be pressed into scientific speculation. In the end, the ancient Indian texts that mention Vimanas do not offer a blueprint for technical flight. They offer something perhaps deeper, a recognition that the sky is not just a physical frontier but a realm of imagination, meaning, and poetic possibility, a place where human curiosity first began to soar. From the weed-choked riverbeds of ancient empires to the carved stone floors of forgotten palaces buried beneath the rubble of millennia, there are clues that ancient engineers wrestled with the same mechanical problems that confront us today: friction, motion, and the controlled transfer of force. Here, in the silent testimony of shaped spheres and rotating platforms, we seek the echoes of mechanical ideas that hint at knowledge either lost or never fully recognized. What does it mean when we find spherical elements that resemble bearings, or articulation points that mirror modern ball joints? Do these constitute primitive machines, symbolic echoes, or early solutions to the very real challenge of motion? In modern engineering, the ball joint and the bearing are core mechanical elements. A ball joint is a spherical interface that allows multi-axial motion between two components. Think of the human hip or shoulder, where a rounded bone fits snugly into a cup-like socket, enabling rotation and a wide range of movement about a common center. The bearing, in its most basic sense, is a support structure that allows smooth, low-friction motion between two elements, whether that motion is rotational or linear. Bearings reduce friction and wear by allowing surfaces to slide or roll with minimal resistance, and they are foundational in anything that turns, a wheel, a gear, or even a pulley. Yet in ancient archaeology, discovering mechanical analogues to these elements is rare and often contested. Most early human societies solved motion problems not with precision steel balls or machined races, but with ingenious designs rooted in materials and principles available to them. The Egyptians used sledges and wetted sand to ease the movement of heavy blocks, effectively reducing friction without any formal rolling or ball element. They also depicted simple plain bearings in drawings of hand drills, where rotational motion was supported and guided by a fixed point, one of the earliest explicit representations of mechanical support in the archaeological record. Such plain bearings supported rotating drill shafts and demonstrate that ancient craftsmen understood the need to manage friction at moving interfaces, even if they lacked the later sophistication of rolling elements. Among the few genuinely compelling mechanical bearers of ancient bearing-like technology are the enigmatic remains of the Roman ships recovered from Lake Nemi near Rome. These lavish ceremonial vessels, built in the 1st century AD and raised from the lakebed in the early 20th century, contained fragments that engineers now recognize as rolling element supports, essentially early bearings. Some platforms on those ships were mounted on bronze balls held in shallow sockets, forming a type of thrust bearing that allowed a heavy platform to rotate with surprisingly little friction. The surviving bronze spheres, some polished by turning on a lathe, with wear patterns visible where they once bore weight, are remarkably similar in function to what modern mechanical engineers call a bearing. These rotating platforms, likely used to display statues or heavy objects, capitalized on the principle that spherical elements between two surfaces can distribute load and allow smooth motion with reduced friction. The importance of the Nemi finds cannot be overstated. Prior to this discovery, history textbooks assumed that rolling element bearings were later inventions, emerging with the scientific revolution and industrialization. But here, dated to the 1st century AD, are components that physically resonate with the same mechanical logic, loads supported on spheres between races that allow rotation. Whether or not the ancients fully understood the mathematical formalism of friction reduction, they demonstrably applied its effect. These Roman bearings were not isolated curiosities. They were part of a working mechanical environment that reflects a practical solution to an engineering problem very similar to those faced by later designers. Outside of the Mediterranean world, evidence for bearing-like elements is far more speculative. Some archaeologists and engineers note that Neolithic carved stone balls, found predominantly in Scotland, date back to between roughly 3,200 and 2,500 BC and are smooth, rounded, and sometimes intricately worked. Ideas about their function range from weaponry or ceremonial objects to the provocative suggestion that they might have served as primitive ball bearings for moving heavy objects, a notion based on the principle that a sphere can facilitate motion under load. However, the archaeological context for these stone balls is not clearly mechanical. They are most often found singly, rarely part of a known mechanism, and show little direct wear consistent with rolling under heavy loads. Thus, while intriguing, there is no confirmed evidence that they were used as mechanical bearings in ancient machinery. Indeed, the history of bearings before the modern era is one of gradual innovation rather than sudden leaps. Even before the Roman examples, early civilizations used roller elements in the broadest sense. Wooden logs under sledges or leather loops supporting axles reduced friction by turning sliding motion into rolling motion. These rudimentary bearings allowed large stone blocks to be moved more easily during pyramid construction and other monumental building projects, effectively acknowledging the same tribological principle that underlies modern bearings: turn motion into rolling to reduce friction. But these were not ball bearings as we understand them. They were designed motion aids born of necessity and empirical observation. In contrast to rolling bearings, the ball joint in mechanical engineering allows a component to pivot about a spherical surface. In nature, ball and socket joints are seen in vertebrate anatomy, the hip and shoulder, where a rounded bone end fits into a complementary depression, allowing controlled motion in multiple directions. Mechanically, this concept is used today in suspension systems, universal joint linkages, and pivoted interfaces where flexibility and load transfer must coexist without binding. The idea is simple. A ball articulating in a socket enables motion along many axes while distributing load. In the archaeological record, explicit mechanical ball joints, where two metal components articulate via a spherical interface, are exceedingly rare. Most ancient joinery techniques, such as mortise and tenon or pegged wood joints, solved motion constraints or load transfer without spherical interfaces. Even advanced ancient machines like the Antikythera mechanism used gears and axles, but not ball joints as we understand them today. Their rotary motion was managed with plain bearing surfaces and press fits, not spherical pivots.
Yet the conceptual resonance is notable. The Romans, as shown by the Nemi ship platforms, used spherical elements to support rotation under load. The fact that these elements were manufactured bronze spheres fitted into sockets and capable of bearing significant weight hints at not merely artistic form, but mechanical intent. A silent acknowledgement of the benefits of spherical support in rotational contexts. Whether the designers called them bearings or simply part of a rotating platform is unknown, but the physical evidence speaks of a practical problem solved in a way that anticipates later engineering developments.
In landscapes far from Italy, similar mechanical signatures are rarer and harder to interpret. Some ancient Near Eastern drills from the 3rd millennium BC included components that acted as sockets and flyweights, facilitating rotary motion for drilling operations, but these were improvements on human power tools rather than precision bearings or ball joints. Likewise, the absence of direct textual evidence for engineered pivots or bearings in many ancient cultures underscores that such techniques were practical solutions, not formalized technologies embedded in treatises or technical manuals. The legacy of these hidden mechanical signatures, the spheres that bear load, the joints that articulate motion, is not that ancient engineers had fully fledged knowledge of tribology or mechanical design as we define it today. Rather, it is that the problems they faced were universal: friction, rotation, and motion. Sometimes their solutions approached the logic of later engineering, sometimes they remained empirical, domain-specific applications of broad principles. In the Roman ships of Nemi, we see the most compelling archaeological evidence that spheres were used to support motion in a way strikingly similar to modern bearings. Elsewhere we find hints and echoes, but the absence of explicit articulation or systematic design leaves room for debate. What is undeniable, though, is the persistence of certain ideas. At the heart of many mechanical dilemmas lies the simple challenge of how to make one thing turn smoothly against another. That challenge, encountered by crafters, builders, and engineers across the ancient world, is where the hidden signatures of motion begin to whisper across the centuries. If you are liking the journey, consider subscribing to more in-depth scientific and psychological journeys. In the myths of ancient civilizations, movement is everywhere. Gods ascend, chariots roll across the heavens, celestial spheres revolve in perfect harmony. At first glance, these stories seem poetic, symbolic, or allegorical. Yet a closer examination reveals recurring motifs that suggest more than metaphor. They echo the principles of mechanical motion familiar to engineers today. Among these, patterns resembling pistons and flywheels emerge repeatedly, woven into narrative, ritual, and artistic representation. In Mesopotamia, texts from Babylonian and Assyrian archives describe devices for moving water and lifting weights. Some tablets speak of oscillating beams, reciprocating arms, and rotating drums, described in language that, though mythic, can be interpreted mechanically. One passage from a Sumerian incantation describes a wheel that drives the waters, its motion cyclical and balanced. Scholars who study these passages note that the verbs and metaphors often imply controlled, repeated movement, akin to the linear to rotary motion conversion found in Pistons. While no physical example survives, the conceptual understanding is unmistakable. The ancients recognized how reciprocating motion could drive rotational energy, at least in principle. In Egypt, the coffin texts and temple inscriptions occasionally employ language describing the movement of divine chariots and sunboats. In some ritual texts, the sun is said to push the axis forward with steady revolutions, a phrase that could be read as an allegory for rotational mechanics. Mechanical historians suggest that these descriptions might encode primitive awareness of energy storage and transfer, principles later formalized in flywheels. The repetition and rhythm in ceremonial depictions, such as rotating shrines or statues, indicate an appreciation for inertia, momentum, and balance, the very phenomena that allow a flywheel to smooth oscillations in motion. India provides perhaps the most vivid examples. Ancient Sanskrit texts, particularly those describing vimanas and other aerial vehicles, include references to shafts, rotating discs, and devices that transfer motion in a cyclical manner. Terms like chakra and pradakshina denote circular motion and are often coupled with descriptions of force, balance, and equilibrium. Some passages describe rotating elements that drive other components, conceptually mirroring crank and flywheel arrangements, even if the texts are primarily allegorical. Scholars argue that these descriptions are not random. The repeated references to rotation, angular momentum, and counterweights suggest embedded mechanical logic encoded in the language of myth. The Greeks, too, left traces of mechanical thinking in their philosophical and literary corpus. Hero of Alexandria's texts, written centuries later, formalized concepts like steam-driven oscillators, rotating spheres, and centrifugal systems. Yet earlier Greek myths, such as chariots of Helios or Hephaestus automata, frequently describe repeated motion that is systematically regulated. Mechanical historians posit that these narratives preserve collective memory of empirical observations. Gears, reciprocating arms, and rotating mechanisms may have existed in rudimentary form, their function transposed into the language of divine craft. The principle is familiar to modern engineers. If you wish to transmit energy smoothly and cyclically, you rely on flywheel-like inertia and reciprocating motion. The ancients may have encoded these ideas in metaphor. Experimental studies have attempted to bridge myth and mechanism. By modeling descriptions from texts, engineers can reconstruct plausible mechanisms for moving water, rotating ritual platforms, or operating automata. Reciprocating rods connected to weighted arms can generate smooth oscillatory motion, stored and released by flywheel equivalents. In certain reconstructions of temple machinery, circular drums and weighted shafts replicate the rhythm described in inscriptions. While it is impossible to prove that these devices existed physically, the mathematical and mechanical consistency of the reconstructions demonstrates that the ancients had the conceptual tools to understand oscillatory systems and energy storage. The key lies in the repeated language of motion. Phrases describing rotation around the pivot, back and forth, or carried steadily by force, indicate awareness of load distribution and cyclical transfer of energy. Pistons, in essence, convert linear motion into rotation. Flywheels store rotational energy and release it smoothly. Texts that describe levers, ropes, weights, and rotating drums, sometimes in allegorical terms, hint that these mechanical principles were known, if not formalized. The combination of repetition, symmetry, and timing in mythic narratives may reflect practical knowledge transposed into ritual or poetic language, allowing mechanical ideas to persist even as physical artifacts vanished. In some cases, art corroborates the textual evidence. Reliefs in India and the Mediterranean show circular discs with radial spokes, oscillating arms and cranks, features consistent with piston flywheel systems. In Anatolia and Greece, certain ceremonial platforms reveal pivot points and weighted shafts, likely designed to rotate smoothly and return to starting positions, a function directly analogous to a flywheel storing and regulating motion. Even if these platforms were primarily symbolic or ritualistic, the engineering principles embedded in their design are clear: balanced rotation, momentum transfer, and controlled oscillation. The broader implication is striking. Across cultures, myths and ritual texts may serve as repositories for mechanical knowledge, encoding principles of motion in metaphorical language that modern engineers can decode. Pistons, cranks and flywheels appear repeatedly, not as blueprints but as conceptual scaffolds. They preserve understanding of energy, rotation and cyclical motion in forms intelligible to those attuned to mechanics. In this sense, myth becomes not merely narrative but a vehicle for preserving engineering insight across generations, a bridge between observation, imagination, and application. As we trace these threads from Mesopotamia to Egypt, India to Greece, a pattern emerges. Human cognition has long grappled with the problem of motion. The ancient mind sought to understand how to store energy, convert linear force into rotation, and maintain equilibrium in dynamic systems. Whether this knowledge was applied in functional machines or preserved in stories and ritual, the underlying logic is mechanically coherent. It anticipates concepts that would only be formalized thousands of years later in the age of engines and industrial design. And so we arrive at a central question. Were these descriptions of pistons and flywheels purely metaphorical, or did they encode practical understanding, passed down through myth and ritual to guide artisans and engineers long before written mechanics existed? Perhaps ancient peoples did not need modern tools to recognize the principles of inertia, rotation, and energy storage. Perhaps through observation of nature, celestial motion, and human ingenuity, they discovered the rules of motion and embedded them in the language of the divine. Whether metaphor or mechanism, the ancient myths whisper a truth that continues to challenge us. Knowledge can exist in forms beyond the physical, principles can survive in poetry, and mechanical insight may have flowed through the minds of our ancestors long before it ever touched metal. The motion described in these stories, piston-like, cyclical, rotational, is not merely symbolic. It is a shadow of engineering thought, preserved in myth, waiting to be understood. Across the millennia, the hand of the artisan has sought to impose order upon the world, to translate the chaos of nature into patterns both elegant and precise. The Sabu disc, recovered from Saqqara, the fragments of Hittite gear-like components from Anatolia, and the interlocking wheels of the Antikythera mechanism all share something remarkable, a geometrical sophistication that suggests knowledge far beyond mere aesthetics. These artifacts are not simply decorative or symbolic, they demonstrate proportions, alignments, and relationships that behave like mechanical constructs, anticipatory of design principles used in much later engineering. The Sabu disc, with its tri-lobed symmetry and central hub, is a perfect case in point. Its lobes are arranged at angles of roughly 120 degrees, forming a rotationally balanced object. Mechanical engineers note that such balance is critical in rotating machinery. When mass is evenly distributed around a pivot, wobble and uneven stress are minimized. The curvature of the lobes, tapering towards the center, mirrors the logic behind impellers and flywheels. Scholars who model the disc in 3 dimensions observe that the radii of the lobes and the diameter of the central hole maintain precise ratios. These ratios are not arbitrary. They align with principles of moment of inertia, governing how rotational energy is stored and released. The disc's geometry ensures that any rotation is stable, even if the object were to spin at moderate speed. The result is a construct that behaves mechanically, whether or not it was ever intended to. Hittite gear-like components, often overlooked in broader archaeological surveys, reveal similar precision. Some bronze fragments exhibit teeth with consistent spacing and uniform profiles, suggesting knowledge of gear ratios, the relationship between driving and driven elements in rotational systems. Ball joints, sockets, and pivot points carved in stone or bronze indicate an awareness of axis alignment, tolerances, and load distribution. When modern engineers reconstruct these fragments digitally, the proposed assemblies show the same balance principles as the Sabu disk: weight distribution aligned with pivot points, symmetry reducing torsion, and geometrical ratios maintaining functional coherence. These principles are not decorative, they are foundational to mechanical stability. The Antikythera mechanism, of course, represents the apex of this geometrical sophistication. Its gears, some with more than 60 teeth, mesh in exact ratios to calculate lunar, solar, and planetary cycles. The spacing and alignment of the teeth follow precise angular relationships, ensuring smooth transmission of motion. When X-ray tomography and computational reconstructions are applied, the mechanisms reveal an intricate understanding of epicyclic gearing, a form of motion mathematics that would not reappear in European engineering until the Renaissance. Here, geometry is inseparable from function. The angle of each tooth, the diameter of each gear, and the placement of shafts all adhere to mathematical ratios that produce predictable, measurable motion. What is striking across these examples is the recurrence of proportions that reflect sacred geometry. Triangles, circles, and polygons appear not only as artistic motifs, but as functional guides. The Sabu disk's tri-lobed form echoes the stability of equilateral divisions. Hittite sockets and pivots conform to circular arcs that minimize stress. Antikythera gears use ratios that approximate harmonic relationships. Mathematicians suggest that this alignment between geometry and mechanics is not accidental. In many ancient cultures, cosmic order was conceived in terms of numbers and shapes, ratios that governed planetary motion, musical harmony, and architectural design. Could it be that the same ratios, intended to reflect universal principles, were also applied to mechanical devices? Consider the mathematics underlying rotational balance. In any spinning object, the distribution of mass relative to the axis defines angular momentum. Unequal spacing creates torque imbalances, causing vibration or premature wear. Artisans of the Sabu disk may not have formalized the equations, but their selection of lobes, angles, and diameters reflects an intuitive understanding. Equal mass distribution produces stability. Similarly, the Hittite fragment's spacing of gear-like teeth corresponds to integer ratios, precisely what allows meshing wheels to maintain continuous motion without slipping. The Antikythera mechanism codifies these principles, with each gear's size mathematically derived to produce exact orbital predictions. In all three cases, geometry is the medium through which motion is controlled and predicted. Beyond rotation, the principles of translation and leverage appear encoded in these objects. The Sabu disk's hub implies a mounting shaft. Hittite pivot points suggest linear to rotary motion conversion. Antikythera's interconnected gears translate one rotational axis into multiple correlated movements. The mathematical sophistication required for these translations is considerable. In modern mechanical engineering, these calculations are expressed using ratios, angles, and torque equations. In antiquity, these same relationships were realized empirically through proportion, observation, and iteration. The artifacts reveal a logic of motion embedded in geometry itself, a logic that mirrors physical reality with astonishing fidelity. Sacred geometry is more than pattern. It is an applied philosophy of balance and proportion. Ancient architects used it to align temples to solstices, orient pyramids, and design harmonious facades. In the mechanical domain, the same principles govern rotational stability, gear ratios, and energy transmission. Mathematicians analyzing the Sabu disk note that the lobe's curvature can be described by conic sections, producing rotational flow patterns that are stable and uniform. Hittite gears follow similar angular mathematics, with teeth spacing corresponding to simple fractions that would allow continuous movement without interference. Even without textual explanation, the geometry of these objects enforces functionality. The implications are profound. Across disparate cultures and millennia, artisans and engineers encoded motion into form. Geometry was both symbolic and operational. Circular symmetry, angular ratios, and harmonic relationships were not merely decorative. They were the language through which mechanical knowledge was preserved. Observing these patterns today, modern engineers can reconstruct functional principles centuries ahead of documented technological history. Yet the deeper question emerges: did ancient craftsmen consciously understand these principles in the abstract, or did observation and tradition produce effective results intuitively? Perhaps sacred mathematics, intended to harmonize humans with cosmic order, naturally aligned with physical laws governing motion. Or perhaps some knowledge of mechanics, rotation, balance, torque, was embedded within these geometric forms, awaiting rediscovery. In either case, the artifacts testify to a convergence of aesthetics, mathematics, and functionality that challenges our understanding of ancient intelligence. As we examine the Sabu disk, the Hittite fragments, and the Antikythera mechanism together, a pattern becomes clear. Geometry is not incidental. It governs mass, motion, and mechanical relationships. It defines ratios, aligns components, and preserves equilibrium. The secret of these machines may lie not in their materials, nor even in their apparent function, but in the mathematics underlying their design, a language as precise as any blueprint, yet encoded in stone, bronze, and Bronze Age ingenuity. And as mathematicians, engineers, and archaeologists continue to decode these proportions, the possibility remains that we are only beginning to understand how deeply intertwined geometry, cosmic observation, and mechanical design were in the minds of our ancestors. The Sabu disk spins in memory, Hittite pivots align in thought, and the Antikythera gears mesh in imagination, all pointing toward a singular truth. Mathematics may have been the hidden engine behind the most enigmatic devices of the ancient world. The Antikythera mechanism has long fascinated scientists as an unparalleled achievement of ancient engineering. Recovered from the Mediterranean shipwreck in 1901, it has been studied for over a century, yet new insights continue to emerge. Recent academic work employing advanced imaging, high-resolution 3D modeling, and computational reconstructions suggests that what we see today may only represent part of a far more sophisticated device. These studies focus on draconic gearing, lunar nodes, and eclipse cycles, features previously absent from the reconstructed model. The original mechanism, composed of at least 30 bronze gears, allowed the calculation of the positions of the sun and moon, as well as the prediction of lunar and solar eclipses. Each gear was meticulously cut, the teeth angled to maintain precise ratios. For decades, these calculations were considered the limit of its capabilities. However, analysis of corroded fragments and newly identified gear remnants hints at additional, previously unrecognized components. Scholars now propose that the mechanism contained specialized gearing to track the draconic month, the period it takes for the moon to return to the same node of its orbit, approximately 27.2122 days, and by extension, the points where lunar eclipses could occur. The significance of draconic gearing cannot be overstated. Predicting eclipses requires more than simply tracking lunar and solar cycles. It requires the calculation of the moon's ascending and descending nodes, the points where its orbit intersects the ecliptic plane. The ancients would have had to understand the difference between the sidereal month, the synodic month, and the draconic month. Each requires a separate set of ratios to align rotational motion correctly. Theoretical reconstructions now indicate that a complex epicyclic gear system may have encoded these intervals. By meshing smaller gears with precisely calculated tooth counts to larger main drives, the mechanism could, in theory, produce a lunar node dial that rotated at a rate synchronized to the true motion of the Moon's orbital nodes. Additionally, the fragments suggest a secondary dial for eclipse prediction, capable of not only signaling the occurrence of an eclipse, but also its type, solar or lunar, total, partial or annular. This would have required careful translation of astronomical knowledge into mechanical ratios. For example, the Moon's orbit is inclined approximately 5 degrees to the ecliptic, and the points where it crosses that plane precess over an 18.6-year cycle known as the Saros cycle. The surviving gears and the theoretical reconstructions of missing ones indicate that the Antikythera mechanism could have accounted for this precession, a level of precision unheard of in any device until the Renaissance. The evidence for these capabilities comes from multiple sources. Some corroded bronze fragments show gear teeth inconsistent with the known reconstructed system. Their size, tooth count, and orientation suggest they were part of miniature epicyclic trains, designed to translate one rotational period into another. Imaging analysis reveals wear patterns on these fragments, hinting that they engaged in continuous motion with other gears. These traces imply a level of mechanical sophistication that mirrors modern astronomical orreries, in which nested rotations model celestial orbits with astonishing precision. Computer simulations provide further insight. By digitally assembling the mechanism, including hypothesized gears, researchers can replicate the motion necessary to track lunar nodes. Each revolution of the primary drive can be translated through a series of smaller interlocking gears into the slow retrograde motion of the nodes, synchronized with the lunar calendar. The resulting model reproduces eclipse cycles remarkably close to what would have been observed in the Hellenistic period, confirming that the missing gears, if real, were not arbitrary. They were essential to the mechanism's predictive power. Perhaps most astonishing is the implication for ancient knowledge. The mathematical understanding required to design such gearing presupposes familiarity with fractional ratios, least common multiples, and orbital mechanics, applied with no theoretical framework in modern notation. Artisans or astronomer engineers would have had to observe, record, and translate empirical astronomical data into mechanical form, designing each gear to correspond with natural phenomena. This suggests a confluence of observational astronomy, geometry, and engineering expertise at a level that defies conventional historical timelines. Moreover, the lost components, when considered alongside existing fragments, suggest modularity and expandability. The mechanism may have been designed with additional functions in mind, predicting planetary positions, modeling irregular lunar motion, or even providing practical calendrical tools for agriculture or ceremonial scheduling. Each gear, tooth, and dial encodes information, a physical manifestation of abstract mathematics. In this light, the Antikythera mechanism is less a single object and more a hand-operated analog computer, combining observation, theory, and craftsmanship into a portable instrument.
The discovery of new fragments also raises questions about the transmission of knowledge. How could such sophisticated design exist in the 1st century BCE, only to vanish and remain undiscovered until a shipwreck revealed it 2 millennia later? Some scholars suggest the mechanism represents a peak of Hellenistic ingenuity, possibly created in Rhodes or Alexandria, where mathematicians like Hipparchus were active. The precision of gear cutting, alignment of shafts, and understanding of cyclic motion implies workshops capable of high-accuracy bronze casting and mechanical assembly, skills that would not be systematically documented again until the European Renaissance. The physical logic of the mechanism mirrors its mathematical logic. Gears operate with precise engagement angles. The spacing of teeth ensures smooth transmission without slippage. Smaller gears amplify or reduce rotation proportionally, while nested epicyclic systems translate circular motion into slowly precessing or retrograding motion. Each component must be aligned with micron-scale precision to avoid cumulative error over years of simulated motion. That the ancients achieved this by hand
with tools available in the Hellenistic period, underscores a level of mechanical intuition as impressive as it is enigmatic. Finally, these insights invite a reconsideration of ancient scientific culture. The Antikythera mechanism, particularly with these hypothetical lost fragments, is not merely a calendar or a novelty. It represents a systematic application of observation, mathematics, and mechanics. The ability to calculate lunar nodes and eclipse geometry centuries before such calculations were codified in modern science demonstrates that Hellenistic engineers were thinking in terms of functions, variables, and ratios, concepts fundamental to later computational devices. And so, as scholars continue to scan fragments, reconstruct gear trains, and simulate motion, the Antikythera mechanism continues to reveal its secrets. Its missing parts hint at knowledge deeper than what survives in the bronze fragments recovered from the sea. Perhaps the device we hold in our hands today is merely a fragment of a grander intellectual edifice, a window into the mind of an engineer or astronomer who understood the cosmos through the elegant language of gears, ratios, and cyclical motion. The question that lingers, haunting the reconstruction efforts, is simple and profound. What if we have only glimpsed the tip of the mechanism's intellectual iceberg? What other functions, calculations, or insights lie hidden in fragments still lost to time? In contemplating this, we are reminded that human ingenuity may have achieved wonders in antiquity that remain just beyond the reach of our understanding. The deserts of Upper Egypt conceal secrets not only in monumental architecture, but in objects of subtle elegance. In 2023, high-resolution 3D scanning of pre-dynastic stone vessels revealed details invisible to the naked eye: tool marks, perfectly concentric surfaces, and geometric symmetry that defy conventional expectations for the period. These vessels, carved from schist, diorite, and other hard stones, exhibit tolerances remarkably close to what modern precision engineers would consider functional accuracy. The surfaces are uniformly smooth, the walls even, the central axes perfectly aligned. Such precision is difficult to achieve even with modern hand tools, let alone with copper chisels, abrasives, and rudimentary grinding implements available 5,000 years ago. Analysis of the tool marks indicates highly controlled motion. Lines suggest rotational turning, perhaps on rudimentary lathes or turning devices, combined with carefully measured abrasions. In several vessels, the inner curvature matches exact mathematical profiles, akin to what engineers today call a parabolic or circular section, where deviation from the intended curve is measured in fractions of a millimeter. These profiles are not decorative, they behave mechanically. Fluid experiments with replicas show that some shapes could control flow or rotational dynamics in ways that hint at functional understanding of forces acting on solids and liquids. Beyond practicality, the symmetry and alignment raise profound questions. Pre-dynastic workshops may have had standardized methods for producing objects with consistent axes and surface finishes. Was this the result of ritualized perfection, an aesthetic pursuit, or empirical knowledge that anticipated principles of rotation and balance found in much later metalworking and machinery? Some scholars propose that these vessels, by demonstrating mastery of rotational symmetry and tool control, hint at a mechanical intuition, an understanding of how rotational forces and balance operate that would only reappear centuries later in Greek and Roman engineering. Material choice further complicates the picture. Schist and diorite are brittle and prone to flaking. Achieving such uniformity without catastrophic fracture indicates not only technical skill, but deep familiarity with material properties. Craftsmen may have understood how to manipulate pressure, speed, and abrasive materials to produce reliable results. In effect, they may have been operating with principles analogous to modern machining processes centuries before the formal study of mechanics. The 2023 scans have reignited debate. Were these vessels purely symbolic, a pursuit of idealized geometry reflecting cosmic or ritual order? Or were they functional, representing experimental proto-machinery, tools or components designed with mechanical properties in mind? The data alone cannot answer this fully, but it underscores a persistent truth. Egyptian artisans were capable of precision that challenges our assumptions about technological progression. And so, as we trace the perfectly aligned axes, the smooth interiors, and the subtle mathematical ratios embedded in these stones, the question lingers: did the Egyptians master techniques we still struggle to explain, or have we merely lost the context to understand their full ingenuity? Across the ancient world, remarkable mechanical artifacts appear in widely separated cultures. The Antikythera mechanism in Greece, Hittite gear fragments in Anatolia, the Sabu disc in Egypt, and references to Vimana-like mechanical reliefs in India all exhibit precision, symmetry, and an understanding of motion that challenges conventional timelines. Each discovery is extraordinary on its own, but when viewed collectively, a question emerges. Were these isolated feats of ingenuity or evidence of cross-cultural transmission of technical knowledge? Trade networks in the ancient world were extensive. Mesopotamian cities traded with the Indus Valley, the Mediterranean engaged in commerce with Egypt, and Anatolia sat at a crossroads of Eurasian exchange. Goods, ideas, and skilled artisans moved along these routes. It is plausible that technical knowledge, mathematical ratios, geometrical design principles, and mechanical intuition could have traveled alongside commodities such as metals, spices, or textiles. The notion of independent invention becomes harder to sustain when similar mechanical patterns appear across regions separated by thousands of kilometers. Anthropologists and historians note that convergence does not always imply direct contact. Some similarities may arise from shared cognitive frameworks, humans independently identifying efficient solutions to universal problems. Rotational symmetry, gear ratios, and balanced motion are mathematically optimal for transmitting force, tracking celestial bodies, or creating repeating cycles. Yet the sophistication and consistency of certain artifacts, particularly complex gearing systems like the Antikythera mechanism or precision carvings in Egyptian vessels, suggest more than coincidental alignment. Archaeological evidence provides additional clues. Material analyses reveal trade in metals and tools capable of fine craftsmanship, such as copper alloys for cutting bronze gears or abrasives for shaping hardstone. Written records from Mesopotamia, though silent on electricity, mathematics, or gear design in mechanical form, attest to knowledge of weights, measures, and cyclical calculations, prerequisites for more complex engineering. In India, iconography of Vimana-style vehicles and mechanical motifs hints at a conceptual understanding of motion, possibly codified in ritual or technical knowledge now lost. The question remains whether these societies were entirely independent innovators or whether ideas diffused through a network, formal or informal, of artisan knowledge. Could there have been itinerant engineers or workshops that spread mechanical principles across continents? Or does the recurrence of specific patterns reflect a deep cultural memory, a shared mental template of what motion and mechanics could achieve, encoded in ritual, architecture, and artifact design? The patterns are striking. Across cultures, we see attention to rotation, balance, gearing, and symmetry, all suggesting sophisticated observation of nature. The artifacts imply a technical vocabulary shared in some form, whether through direct instruction, imitation, or parallel reasoning. Yet the absence of explicit documentation, instruction manuals, or continuous material tradition leaves the connection tantalizingly ambiguous. As we trace these threads from Mesopotamia to the Mediterranean to India, a subtle yet persistent question surfaces. The patterns connect, but to what origin? Were these innovations convergent echoes of human ingenuity or evidence of a network of mechanical knowledge now lost to history? The answer remains shrouded, yet the resonance of precision and design across continents hints at a world far more interconnected than previously imagined. Across continents and millennia, we encounter objects whose existence forces a confrontation with human assumptions: the Antikythera mechanism, the Sabu disk, Hittite gear fragments, and Baghdad batteries. Each possesses a duality that challenges categorization. Were they practical machines designed to perform specific functions or symbolic constructions, encoding abstract cosmology, ritual significance, or philosophical principles? Archaeologists emphasize context. Many artifacts were discovered in tombs, temples, or ritual sites. The Sabu disk lay in a burial chamber surrounded by funerary goods, while some Hittite gear fragments were found amidst domestic or ceremonial debris. To the traditional lens, context implies symbolism. These objects served as metaphors or as ceremonial tools intended to accompany the dead, represent cosmic cycles, or reflect societal hierarchies. In this view, mechanical resemblance is coincidental, or at best an aesthetic choice. Engineers, in contrast, cannot ignore the precision embedded in these objects. Tooth counts on the Antikythera gears match astronomical cycles with near-perfect accuracy. The Sabu disk demonstrates balanced radial symmetry consistent with rotational stability. The Baghdad battery, if interpreted as functional, embodies the basic principles of electrochemistry. For modern technical minds, such deliberate patterns suggest intentionality that transcends symbolic artistry. Mechanical function, however rudimentary or experimental, cannot be dismissed easily. Philosophers of science highlight the tension between observation and inference. The artifacts demand interpretation, yet human bias inclines us toward familiar frameworks. Do we see a machine because we expect one, or are we missing the point of an object that is simultaneously aesthetic, symbolic, and technical? This middle ground may be the key. Perhaps the ancients encoded practical mechanical principles into forms that also served ritual or social functions. Function and symbolism were not mutually exclusive. In early societies, one could reinforce the other. Experimental reconstructions provide insight, yet even they raise questions. Replicas of the Sabu disk rotate smoothly and interact with fluid dynamics. Recreated Baghdad batteries produce measurable voltage. Theoretical Antikythera components calculate lunar nodes with astonishing accuracy. Still, these simulations cannot prove use. No inscriptions, manuals, or continuous tradition confirm intentional operation. And yet, the precision is too exact to ignore. These artifacts may have functioned experimentally or conceptually, embodying principles that were understood but never widely codified. The debate is amplified by absence. In many cases, the knowledge appears isolated, surviving in a single vessel, fragment, or mechanism. Scholars ask, if ancient peoples grasped mechanical principles, why did that knowledge vanish? Was it forgotten, suppressed, lost through societal collapse, or never fully transmitted? The question extends beyond archaeology. It touches cognition, culture, and the fragility of human memory. The objects force us to consider not just what people knew, but how knowledge is recorded, preserved, and transmitted. Were we witnessing the remnants of early engineering brilliance, or the echoes of ritualized abstraction shaped by empirical observation? Human history is replete with vanished arts. Entire technologies have disappeared, not due to alien intervention, but through the normal cycles of civilization. Crafts are lost when societies collapse, materials are repurposed, or apprentices fail to transmit knowledge. Metals are melted, tools vanish, and techniques fade from memory. The evidence that survives, whether bronze gears, stone discs, or clay jars, offers glimpses into capabilities that once flourished and then disappeared. Consider bronze casting, or the precise turning of hard stone. These skills required not only tools, but systematic empirical knowledge, how pressure, abrasion, and material behavior interact over repeated trials. If the social structures sustaining these practices crumble, so too can the knowledge itself. A single surviving artifact may be the only remnant of a larger technological tradition, preserved accidentally rather than intentionally. Philosophers ask whether absence of evidence equals absence of capability. The Antikythera mechanism challenges assumptions precisely because nothing else survives in Hellenistic engineering of comparable complexity. The Sabu disk suggests knowledge of rotation and balance in Egypt before widespread mechanical systems existed. Baghdad batteries hint at electrochemical principles long before systematic electrical theory. In each case, what remains may be a fragment, not a failure, a witness to ingenuity lost to time rather than an anomaly created in isolation. These ghosts are also human stories. They reflect observation, experimentation, and the ambition to harness principles of nature, motion, energy, celestial cycles, through artifacts that are part functional, part symbolic. The mechanisms remind us that humans have long sought to understand and shape the world, yet the record is inevitably incomplete. Civilization forgets as much as it remembers, and so the narrative turns inward. The final artifact emerges not from a tomb or ruin, but from the imagination and ingenuity of an ancient engineer. It is a testament to human curiosity and capability, preserved in bronze, stone, and clay, waiting for eyes capable of perceiving its significance. Across millennia, these fragments call to us, reminding us that invention can be transient, knowledge fragile, and yet the human mind remains capable of profound insight, insight that, even when lost, resonates through the echoes of time. Across deserts, seas, and forgotten tombs, we have traced traces of ingenuity that defy conventional timelines. Bronze gears submerged for millennia, stone discs carved with rotational mastery, clay jars capable of generating electricity. These artifacts speak not only of what was built, but of what the human mind could imagine, calculate, and execute long before we believed such capabilities existed. They are invitations, each fragment a silent question, challenging assumptions about the linear progression of technology. When we examine the Antikythera mechanism, we see a civilization capable of modeling celestial movements with precision that would not be repeated for over 1,000 years. The Sabu disk demonstrates an understanding of balance, symmetry, and rotational geometry at a time when mechanized thinking was presumed non-existent. Hittite gear fragments hint at rotational and interlocking mechanisms that suggest observation of motion and force, while Baghdad batteries reveal that principles of electrochemistry could have been grasped centuries before formal science codified them. Across these disparate artifacts, the patterns are consistent. Ancient minds could encode empirical understanding in forms that survive as relics today. Yet the true revelation lies in perspective. These discoveries do not merely add footnotes to history, they demand that we reconsider the narrative of human capability. Innovation is not strictly cumulative, not always linear, and not always fully preserved. Civilizations rise and fall, knowledge is lost and rediscovered, and ideas may leap across regions, cultures, and centuries in ways that leave only traces for us to reconstruct. What we call anomalies are often evidence of ingenuity now obscured. Fragments of technological thinking that do not fit neatly into textbooks, but nonetheless reveal a continuity of human curiosity. The implications extend beyond machinery. They touch on philosophy, cognition, and the way we perceive progress. If mechanical reasoning existed thousands of years earlier than previously assumed, we must ask what other aspects of human capability remain hidden, obscured by the passage of time, the fragility of materials, or the impermanence of records. Perhaps our understanding of mathematics, engineering, and observation is only a shadow of what was once explored. Perhaps our ancestors grasped principles we are only beginning to comprehend. Ultimately, these artifacts awaken a larger truth. Human innovation is not bounded by chronology, nor defined solely by surviving documentation. It is a living, evolving force, sometimes fleeting, sometimes enduring, always capable of inspiring wonder. The gears, discs, and jars we have seen do not end the mystery. They illuminate it, urging us to question, explore, and reimagine what is possible. And so, as we leave behind the ruins, the ocean depths, and the tombs, the final question remains. If mechanical thinking was present millennia ago, what else lies hidden, waiting to challenge our assumptions? How does this reshape our understanding of ourselves, our ingenuity, and the legacy of human thought? The mystery does not conclude. It awakens, inviting each of us to look closer, think deeper, and recognize that the dawn of discovery is never finished. The shocking fact is, these are not the only ancient machines that shocked scientists. We have discussed a few others in Part 1, present on our channel. Lastly, thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.